Good morning and welcome to Advetec. My name's Jim Lovett, I'm the Chief Executive, and I'm delighted to welcome you here to our Southwick offices for a live video demonstration.
So what we're going to do today, guys, is we're going to walk you through our Advetec technology. We're going to start by just walking you through a small demonstration unit that we've got operating today, which is processing some black bag waste. So what the system is doing here, in order for us to process waste into our system, we first of all need to precondition it. And what I mean by that is we need to take the waste and we need to put it through a shredder and knock the particle size down to about 80 millimeters in size. So this is some black bag waste which has been through the shredder and has been shredded. We use a 4-shaft shredder with an 80 millimeter screen that allows us to get that particle size. Now the particle size is important to us for several reasons. Firstly, this is an aerobic process, so we've got to be able to get oxygen into the process, and we've also got to be able to liberate water that's inherent within the waste. So if we have just put waste in as it is with long pieces of plastic, that can have the effect of binding the mass together, which will give us a problem. So the shredded material gives us that particle size, so as it's processed, it opens up, we get the oxygen in, we get a strong aerobic biomass, and that's how our process operates. So once the waste has been shredded here, it'll get loaded into an auger. On our systems, we use a centerless auger, which means that it's basically an Archimedes screw with no shaft through the center. The reason we use centerless screws is that we get no entanglement of material around that, so it's virtually maintenance free during the life of its operation on the process. So once it's shredded, it will go into an auger and it then passes up into the XO itself. Now, this is our smallest unit we do. This is the XO3. It'll process up to about 1.5 tons a day of mixed waste. This is 2 chambers. Running through the system, there's a motor drive at one end, which has a shaft that passes through the machine itself, and around that shaft there's a series of paddles. Now, when it goes into process, we do an indexation process on that waste. So we bring it into the process, we then rotate it at about 1 RPM, very slowly in one direction. We then leave it in a position there for a minute, and then we do a reverse rotation. And what that's doing is it's allowing the mass to open, get aerated, and release that water that we talked about. And then the addition of fresh material into the process is then what gives us an indexation of material through the process and then out of the machine several days later. Now, at the same time all that's happening, our biological products, which are all liquid based, are housed in this reservoir here, and then we continually, every day, we add a blend of our biological products, and we also add a biostimulant. And it's the reason we add that biology is there to make sure it's there. And the biostimulant is the very clever piece of what we do, because it speeds up the respiration rate of our biology and allows us to get fast throughput into our systems. So typically for processing mixed black bag waste through one of our systems, you're looking somewhere in the region of about 48-hour processing time from feeding in to coming out the back of the process. So this system here has got a couple of control panels on it, and on those control panels it allows us to put all the settings in for the system itself, so that we can, and you probably can't see that in the sunlight, but it allows us to put all of the settings in for what we call the recipe, and that's how we set the machine up for how it's going to rotate, how much airflow we're going to bring into the system, and then we also program in what heat we want to have in each of the particular chambers. So we set the heat that we want in there. We have a series of heater mats which are wrapped around the system itself, so they help initially begin to get heat into the process to get it kick-started. Our biology starts from an activity point of view at about 20 degrees C, and then it'll operate all the way up to 70 degrees C. So we set the temperature in each of the chambers that we want, and then as the process is operating, we're monitoring the temperature within the biomass itself, and then the heaters will kick in and out of the process to maintain. So for example, if you put a heavy load of wet, say cold waste into it, you'll get a little bit of a drop in temperature at the front of the process. So our heaters will sense that, they'll come back on, they'll add some additional heat into the process and bring it back up to keep a strong biomass in process and operation. We're also monitoring, within the system there's some sensors, so we're monitoring relative humidity within the process, because that's an indication of biological activity that's taking place. So that's quite a key indicator for us. So then at the end of the process, we have a very simple method of just removing material out of our process. There's an end bulkhead contained behind the housing here, and there's an opening in that bulkhead. And as the shafts in the system rotate, then the material as it passes it and it's processed will then fall down that chute. So because this is a demonstration, we don't have all the handling equipment on it, but normally you would have, and again, another centerless auger at this point, which would then take that material over into whatever vessel it needs to do to be removed away from the site in the process. But that's the resultant flock that's come out of the process. So as I say, for this process, this demo, less than 48 hours, we've gone from black bin waste that smells, is full of flies, maggots and all that great stuff, through to we now have a very dry material where we've removed the organic content and as importantly, we've removed that water element that's within the waste itself. So that's now in a condition to go off to other processes.
And the other good thing it's done at this point is actually stabilise the organic material as well, so it won't degrade any further, won't give any further carbon dioxide or methane when it's actually used.
Okay, so that's a very quick demonstration in a very small machine of our process, processing black bag waste. So what we're going to do now is I'm going to take you inside the workshops and I'm just going to give you a quick technical walkthrough of our big XO22 machine and then an XO6 machine that's bound to go off to an NHS site. So come in the workshop, guys. So this is our XO22. It's designed to take up to 10 tons of mixed solid waste a day. It's different in size to the machine that you've just seen outside. It does have 4 chambers in the process itself. But if we just come down to the end, and let me just show you, just to give you an idea of scale of this compared to the other unit. So this is the control panel that's going to get mounted onto the system itself, and the control panel gets mounted here. So this screen that's down here, kind of at my eye height, is going to get mounted up here to this level, so it'll be in here. And then the front end of the system, our in-feed auger that we talked about outside, comes in through this end of the machine, up in through a porthole at this point, and then into the process. Everything's just on a much bigger scale than it was on the smaller system outside. So let me take you back along and talk about some of the design elements of this system itself. So the 22, because of its size, we have on all our systems, we have a green exoskeleton frame, and that serves 2 purposes. So the motors and drives on our system, when they rotate, there's a significant amount of biomass inside the product. And so you need a lot of forces and torques to be able to rotate that and move it. The resultant forces that come from that, you have to be able to deal with that without distorting the frames, or causing problems with the system itself. So the whole of this green frame is designed to take all those resultant forces that come back from those motors turning and put all that force back into ground so that there's no issues. They also then provide the other benefit that you've got to be able to pick this up and move it. And so the system itself has lifting eyes on it, so it can be very easily picked up and moved. And it's of such a strength and design that you can pick it out without any deformation of any of the mechanics inside the system itself, which is important. So the frame is made from mild steel. It's painted with a marine grade paint. So it's got very longevity in terms of when it's in the field and exposed to the elements. All of the inner elements of the system itself, the steel chambers and the shafts and paddles that are inside the system, and they're made from 304 stainless steel. And the reason we do that is obviously processing waste and the resultant water vapor that comes off of it is it's inherently slightly acidic, and when it's hot, that gives you problems with it, just bare mild steel. So the 304 stainless is a key element to us in our design because it can withstand that environment and the corrosion that goes with it. So the system itself is exactly the same as the one outside from a process point of view. This system, the 22, has a shaft that goes from one end to the center and then from the other end to the center. And then our software controls those 2 drive systems together. So it effectively operates as one shaft end to end. But to have this made as one shaft, you've got to, you have to have a supply base that can, machine a shaft that's that long, and that's just impractical. So we go for a 2-shaft solution. In the center point in here, we have some bearings. They're very special bearings that have been designed for extremely long life in application. They have a special coating that's on them. They also have Kevlar seals, and then they have a complete cage arrangement that goes over them to protect them from general pieces of waste that may be passing them. So they're in there, they're floating bearings. The end bearings are fixed in nature. So as the system heats up, obviously you've got stainless steel and mild steel. They have different coefficients of thermal expansion, and so our system is able to deal with that and take up slight movements as it goes, which is why we have fixed and floating bearings within the system. Then the system itself. So this system literally came in a week ago. We just started the wiring process. So as it comes in for fabrication, we then go through a process of fitting all the basket trays that you can see in the bottom of the system. So the guys will do a first stage mechanical fix on this. They'll then lay cables into the system, and at that point there, they then begin to go into the termination process. But then we also, the silicon heater mats I talked about on the small system, those get bonded around the outside of the chambers here. So these chambers here will go through a process where we will remove any particulate matter from them. We'll also then go through a process of degreasing it, and then the silicon heater mats get bonded onto the chambers themselves. And then once that's done, there's some thermal blankets which gets placed across that to ensure that all the heat that's generated by the biomass and from our heaters itself is then kept within the chamber. And then we have thermocouples which are in the heat mats, so we can control and protect the heat mats from overheating. And we also have thermocouples which are then bonded to the chambers themselves so that we can monitor the temperature inside the chamber, which is part of the setup and control of our biomass. So from a reliability point of view, we have nothing in process from a sensor perspective that's going to get hit or damaged, which gives us resilience in operation of the process. So if you try and bury thermocouples inside there with big shafts rotating and waste moving, you run the risk that you'll knock those things off and damage them. So we have everything external, and our software takes care of dealing with any differences we see in terms of thermal differences. So that's the stage that this process is at. There's a series of fans that will get mounted on the system on the top end of it, which will allow fresh air to flush through. And then we also, on the system, we put load cells on it. So this system has 14 load cells on it. They're wired in a particular network, so that if you can imagine when this is outside, we're right to lean on it, or the wind was to blow and buff it against it, the load cells will actually give you some variation in what it's actually reading in process. So the reason we have 14 load cells on there, and the reason we have it wired like it is so that one side of the system, if it's being blown in the wind, can actually see an increase in weight. The other side of the system sees a decrease. We average that across the two, and then we have a piece of software which then smooths that reading come back in. So from an in-process weight measurement point of view, we get a very stable piece of information come back to us from a control point of view. So that's the load cells on the system. All of this will, once it's been cladded, there's then steel covers that go on the outside of this, where all of our cables pass through the bulkheads and out into the outside world. All the cable we use is rodent proof, so it's all protected either in steel jackets or armor braiding, so we don't have issues with any rodents or vermin trying to eat the cables, which they tend to like to do. And where they pass through, we have apertures, and then we have specially shaped plates that come down to close off any gaps so that the little guys can't get in there and feed to their heart's content. And then I say the covers go on the outside. The systems are all designed to be outside. We do have systems that are inside, but it's fundamentally been designed to go outside. We don't care about the ambient temperature conditions because of the thermal lagging that's on the system itself. And so, variations in external temperature are of no concern to us. It's also, the system is IP rated so that it's dust sealed and it can be washed down with a jet washer should you want to. Some customers do, some customers don't. It's a choice for yourselves rather than us, but the system's capable of it. So that's kind of the 22, give you some idea of size and scale. I'm only 5.5 feet, and I'll stick my hand up, but you can kind of get an idea of just how big this thing is. But that's designed to take 10 tons of black bag waste a day into it and be processed. So if we just come up, and then we've got to cover off the back end. So hopefully you guys can get a shot just looking in through the chambers here. You can see the paddles inside. Were I to get inside and stand it, the shaft inside itself is at about this level. It's a 180 millimeter diameter shaft, so it's pretty big inside, and the paddle arms are 2 meters each in radius, so it's a big volume of space that's in there. Then on the back end of the system, exactly the same as the smaller system, we've got a chute here that allows material to exit. It's a very simple process that allows material to fall down. The key is this angle here, and the nature of what we process. This is the optimum angle to allow material to keep falling out. But again, we would have an auger in at this point, which would then take material away into another part of the process. So that, guys, is the XO22 in all its glory. So I'll take you over now, and we can come and see the XO6. So this is the XO6, which is the mid-sized machine between the 3 and the 22. This is designed to take up to 3 tons a day of mixed waste. It's a 3-chamber machine, and you can see the differences between this one and the XO22. So on this machine, we've now started the wiring process has been completed. You can see the thermolation insulation that's gone on. There are stainless steel covers that will come across this, but we've left them off today so you guys can see what's inside. This machine is currently just going through its software testing and electrical test, and then it'll begin to get staged up for its final application. And I'll talk about where this is going and what that application is shortly. So inside the control panels, all the control panels are very similar, but just very different in size because of the nature of the motors. So some of the components will vary to deal with the bigger size of motors that we're using. So again, the cabinets are all sealed. We have air conditioning units that are located on the outside of the unit. So we monitor the temperature inside the cabinet, and then we can control that air temperature in there. Electronics don't get particularly hot, so you've got to keep the electronics at the right temperature. So we monitor the temperature in the cabinet, and the air conditioning unit kicks in and out to maintain it. So if this unit's outside, it's in direct sunlight, our electronics don't care because we're cooling it. It's the best place to be on a hot day, as they say. Thank you. So the system itself, as we say, fundamentally they're all the same. The software is common across the units. It all does the same things. It's just doing it on a bigger machine. So we, in terms of using the system, everything is touch control on this. If I press the right button, it would help. So if you want to go in and look at it, so anybody can come up to the system. You can press overview. You can look at the screen. It gives you a graphical representation of what's happening inside the process. Obviously, there's no motors running. If this motor were to come on, for example, you would see this box where the motor would go green. That would run up to show you exactly what speed it's operating at. And we can, anybody can come along. You can click through here. You can go through the various elements of the system to see what's happening. But if you want to go in and do any changes, you go to an admin setting, but unless you've got the right tag, you can't get into it. So we have access control levels set within our system. So a black tag allows us access into all areas. So I can then go into the system and I can begin to make changes to it. So we mentioned outside about we have what we call a recipe for our system. So we have a module in here called recipe control, and this gives us all the basis of the key points of our system of how we're going to set that up and what that will do in order to process material. Now, this system, if we've got a shred system on board with the unit, then this control panel here will talk to our control panel for the shredder. There's a full safety suite of sensors and interlocks that go between all the systems. So in order for when this system is operational, it will generate a healthy signal, which will be passed to our front end system at the shredder. If there's no healthy signal, then the shredder control panel won't activate and won't allow the system to be operated. So assuming you've got that healthy signal, the shredder can energize and go. So when we commission the system, we go through a process of setting up the different parameters within the recipe. So you've got some fundamental things. So in feed here, we can vary its speed, and we can vary something called overrun time. Now what that is when we've finished, the shredder's finished operating, it'll go into what's called a no load condition. And the no load condition is effectively when the shredder has sensed that it's either processing very soft waste or it's processing waste, or it's finished processing its waste. So that no load point, shredder control panel says, okay, I'm done. So now I'm going to put you into a runoff period. And we will program that runoff period to effectively that if there is soft material in the shredder, it will have enough time to continue to pass that. So once the shredder stops, that will then tell this system that it stopped. And then this system will say, okay, shredder stopped. So now the in-feed system now needs to go into its overrun time. And what that's effectively doing is that any material that's been shredded and has dropped down into that in-feed auger, the overrun time will now allow that to pass up through the auger to make sure the auger is clear of any shredded material and it's inside the process. So that's what we do with in-feed. And again, that's all set as part of the commissioning process. The outfeed on the systems, we can set those up on a timed process. And again, we can vary speed depending upon what the waste is and how it moves. But the time element within that process means that if you put, and just for ease of numbers, let's say you put a ton in and you get a 50% reduction. If you put a ton in, you've got to get effectively half a ton's got to come out every day. So you can set this up on a time basis so that it would just be continually exiting material at various points through the day. But what it also does is these systems, as I said earlier, have got these load cells and this weight control system on there. So we can program into it what our maximum weight is allowed to be in process. And so if the system senses that we're hitting a maximum load because we've just done a heavy load at the front, then the system can actually take control itself of the outfeed, turn that outfeed process, that auger on, and begin to exit material. It'll do that down to a set point condition again, and when it reaches that, it'll then stop. Now it also does another thing, which is, let's say you operate 5 days a week, you're not going to operate at the weekend, so the last thing you want to do is allow the system to empty itself, because then you've got to go and rebuild biomass. So what the system will do is it'll look at the weigh control system, and when it goes down to a minimum weight setting, it'll say, great, I'm at that minimum weigh setting, so now turn off the outfeed auger. Nothing else is to come out of the system. So the system will then hold an amount of biomass resident in process for when you're ready to start reloading waste back into process. So that's the outfeed. The XO drive itself, again here we can vary speed, we can vary how often it rotates forward, how long it dwells and keeps material on the heater mats, and then how much we put it back into reverse. And that forward and reverse rotation is all about, you know, aerating the mass and getting oxygen into it and releasing water that's inherent within the waste. So we play around with those, and they vary depending upon what the waste settings are. And then the chambers themselves, we've got various set points for each of the chambers. So we can set what we want the process temperature to be in each of the chambers. So we set what we want that temperature to be, and then we also set a hysteresis point around that as well. So for example, we would typically set that as a very low number, down in single digits of degrees. And it's quite ironic, because if you think, well, actually it would be better to have a larger hysteresis, because then your heaters won't be on as long, but actually it's the reverse. If you have it where it's too big a hysteresis, you can actually get temperature fall away from the system, and then the heaters have got to be on longer to help maintain it back and pull that together. So we actually use quite a tight hysteresis setting, and what that allows us to do is just very easily just add in additional bursts of heat energies just to keep us at optimum conditions. Now the heaters have some intelligence in them, so there's a lot of heaters across the system, but what we do is they're configured so that they're in zones either on the side or on the bottom of the system. So if one of the sensors says, I've dropped down below the set point hysteresis level, turn back on, what it won't do is turn all the heaters back on the system. It'll just turn the heaters on in the area where you need it. So there's intelligence in there, so we can get optimization of energy usage within the process. And that's quite a key thing to us, because obviously electricity, there's operating costs associated with that. So we have intelligence built into that heating system. And then lastly, within recipe, we have what's called the extraction fan, and that's really about pulling air into the system. And again, we will look at that, look at the waste, understand what levels of humidity we have in and out the system, and then we vary that speed setting. So other bits and pieces we've got, all of our motors on the system are controlled through variable speed drives that we had in the cabinet earlier. So that's these units here. So it's a fixed voltage, vary the frequency on the drive. And that's one of the more energy efficient ways of actually operating the motors, gives us greater control. But what we also do from a safety and a process reliability point of view is we have what's called an anti-blockage mode. Now, because we're using variable speed drives, and if you imagine these systems full of waste, that's a huge amount of material that if the shaft has stopped and you're going to start turning it, it's a lot of material to begin moving. So we can vary and control the acceleration time and the deceleration time. So you avoid that trying to go from 0 to 60 very quickly. You gradually apply power to the shaft and you begin to move it in a controlled fashion so you don't overload and cause problems. We can also vary the sound. Just shut that door for you. We can also vary the sound and the tone of the motors. So we can tune it out. We can make dogs bark if we want to, just by increasing frequency so people can't hear it. So again, we do all that on site so that people have got a noise off of motors that they're all comfortable with. And then the anti-blockage I talked about. So the system here has a maximum current that the motor can accept. And we have a feedback loop that's operating that as it's driving, it gives us a current feedback as to what's happening. Now, if that goes above a certain level for a certain period of time, the system will then put itself into anti-blockage, and it then goes into another piece of software running that will just look at what's now happening with that drive and why it's gone to anti-blockage. So we drop in now another different set of parameters for forward rotation, reverse rotation and speed. And then the drives themselves also have some intelligence in them that we can make use of. So as it encounters that blockage, what the drive will then do is it will apply power to the drive, it'll monitor what's happening with the drive, and then it will gradually increase power with time so that we can effectively overdrive the drive without damaging it to clear the blockage through. And then that whole process will continue for a number of cycles that we program into it. So if for example, you've got very heavy loads going into the system, you can get a heavy load at the front of the system, it's lighter load at the back because it's processed material, then you can see an anti-blockage occur. The last thing you want to happen is the system to stall and trip out at that point. So our anti-blockage system helps deal with that and just kind of work that material through and just alleviate any problems with it. So that's the anti-blockage part of it. And then other elements we've got on the system, there's also vibration monitoring on here. So we monitor the bearings and we look for shock events just in case anything's been knocked or something. So we see that happening. And then we've also got a gas monitoring system on board all the systems. And that's the air that's then coming through our process and eventually exiting. We sniff that air for various gases to see what's happening. Now we sniff for methane, we're not expecting any, but it's a process control thing for us. Because it's an aerobic process, we're not expecting that methane to be there. If it was to stall, then over a period of time, days for example, you may begin to see that. We'll be sniffing for that well below it becomes an issue and know if it's a problem. There's also carbon dioxide, which is a byproduct of our process. So when we load fresh waste into the system, we're looking for carbon dioxide to be created as part of the digestion. And so we can sense for that to see that it's operating. And then VOCs, we sniff for those, and then also hydrogen sulfide. Again, we're not expecting any, it's all control elements and measures. Then all of the information in the system, we have an onboard modem in here which has a SIM card or a LAN connection to it. And so any setting in the system, any data point, any piece of information that's being recorded comes back into the control panel. Any event, any alarm, any alert that takes place, it comes back in, and then our onboard modem system punches that information up into the cloud. So if we do get an alarm or an alert, what that will do is that will send out emails to the engineering team so they can be aware of that and we can get early notification if something's happened. A lot of the alerts we have are just notification and they will self-clear. So if it goes to anti-blockage, for example, we'll understand an event's happened and then we can just check to see what's going on. But then, as I say, if it clears itself, it clears the alert and there's no issues. But then if you do get a hard stop alarm, you get an indication on that. But we also have redundancy built into various systems. So any of the monitoring sensors for process, if they fail, it doesn't stop the process, but we'll get a notification and then we can deal with that. Our fans for bringing air through, that's such a key part of our process that we have dual redundancy on the fans and they run duty and standby. So that if one fan were to fail, the second fan will then take over. We'll get an alarm message saying we can come swap a fan out to deal with that. So redundancy built into the process from that point of view. So there's quite a lot of intelligence going on in here. A lot of software development has been done. And again, this is all talking to our shredder control panels. So that's all linked together and making all that come together. So this system itself here, it's as we say, it's finished wiring. It's now gone into electrical test. This system is going for the NHS at Stoke Mandeville. I haven't got it here today, but so you just need to take my words for this. So on the front end of this system, there will be a shredder, an in-feed auger, and then in front of that, there's going to be a bin lift. And for the guys at Stoke Mandeville, they want to be able to pick several sizes of bin type up. One will be for general, and one will be for food, so they're different sizes. So what the system will do is when the operators come to load waste, again, the shredder control panel has key fobs on it. That key fob only operates the shredder panel, not the XO itself. They will come, they'll release the safety interlock, open the bin lift door. They can then put the bin in, close the door, energize the shredder. When the shredder is operational, they can then lift the bin. So what then happens is the bin will lift itself. It'll get weighed because there's load cells underneath the bin lift itself. It'll weigh the bin with the waste in it. It'll then continue to tip that into the shredder. So it gets shredded, processed, put into the XO. It'll then return the bin back to a set point, weigh it empty, and then drop it to ground, ready for the operators to take out. And at that point there, what the software will then do is it'll take the net weight of what's been loaded. It'll record that into the system. So it'll do a bin count of how many bins that was, what type of bin it was, so we can put sensors on the bins so we know what types of bins they are. So it records that information, puts it into daily accumulators within our software, and then all that information is punched up to the cloud. On the system at the front end at that point, once the bin's been weighed, it'll have a weight, and then there's a light tower on the system which will then go from green to red. So the operators know that they're in inhibit time at that because we've just done a load. And then there's a screen that appears on the shredder control panel that gives them a countdown in minutes until the next bin load that they can do. So it's visual indicators so the guys can see at a distance exactly what the state of the system is and what's happening with it. And then that information that's gone into the cloud, all that gets punched up. If we were to lose data link, so for example, we've got systems in the Bahamas, in the middle of the Atlantic, and it's not unusual to have a lightning storm take a cell mast out there. If that is to occur, what will happen is the control system here will hold 30 days worth of data. When the data link is re-established, all that information then gets ported back up to the cloud, so we don't lose data. It's always in one of two places that we can port it through. And then on the back end of the system here, for Stoke Mandeville, again, we'll have an auger that comes out the back of the system. They're going to move material into an 1100 litre bin for disposal. That'll be within inside a safety cage. The bin is actually on a weigh scale itself, so the cage is completely sealed. There's again a light tower on there, which is green when it's underweight, and then we will pre-program in the weight that the guys are happy to go into the bin itself. When it reaches that maximum weight, that light tower will go from green to red, so they know at that point they need to empty the bin. And then as they go up to the system and they open the doors on that cage, that opening of the doors triggers an event in the software that says weigh the bin. As the bin is then removed, it passes through two sets of sensors that say the bin has now come out. And then when they put the empty bin back in, the same process in reverse, it senses the bins come back in. And then when the cage doors are shut, it then weighs the empty bin, takes one off the other, records that weight out information, puts it back into the system with bin count and weights. And again, that's all punched up to the cloud. And then also from a safety point of view, when they open that cage door, there's a two-stage interlock, which then disables that outfeed auger. So if anybody gets near it, because they're pulling the bin out, there's no moving parts that can be accessed. So it's completely safe from that point of view. So that's the system that's going to go to Stoke Mandeville later this year for installation there. So what we'll do now, guys, is I'll just take you back over to just show you some of our bacterial products. So we talked earlier about the products we had into process. So this is the dry mix of our biostimulant product. And there's a number of secret ingredients in there that we mix, and then we hydrate that on site for putting into the reservoirs on the system itself. So that's the biostimulant product. And then the guy who's doing all the hard work in our process is our bacterial blends. And this is a water-soluble based blend. And I forget the number, but there's hundreds and hundreds of billions of bacterial spores in there that do all the hard work as opposed to the rest of us. So that again gets added with our biostimulant, goes into the reservoirs, and then that gets dispensed into the product every day. So that, guys, is the Advetec XO systems. You've seen the 3622. That's our bacterial product. Thank you very much.
Right, I think we've got some questions coming in on the internet too. Thank you, Stephen. So, first question, I'll probably give this to you, Stephen. What kind of waste can the XO unit process?
So essentially, it can process any waste that's got organic matter in. So if we take the residual waste, which Richard was talking about earlier, even where you've got segregation in place, you find that people are leaving organic matter within that waste. So if it's got organic matter in, like residual waste, perhaps offensive waste, perhaps airside waste, those type of things we can actually process through the XO unit.
Brilliant. Okay. Richard, I shall let you have this one. How long does it take to turn the process into SRF, and how much waste can we load at once?
Okay, so it's a good question. So in terms of time to process, there's a number of factors that would determine that, and it's the moisture content within the waste itself, and it's the amount of organic content. So typically for mixed black bag waste, you're going to be looking at probably less than 48 hours to process from a horrible black bag of smelly waste through to the flock that you saw outside. And I've forgotten the second half of the question.
So how long does it, how much waste can we load at once?
So how much waste can we load at once? So because it's a biological process, if you load too much at once, you can shock the process. So we like to gate control waste going into the process. So again, depending upon the size of the machine, we would look to program it so that over the normal course of a working day, you would feed the waste into the process over what works for the site from an operational point of view. But it will vary from machine to machine. So the XO22, for example, is we will look, typically in an hour, you'll be loading over somewhere between a ton to a ton and a half into the process. But we have again, a suite of sensors and software that helps the operators manage that process.
Brilliant. Okay. Right. What are the terms for the MSA stroke lease, and what does quarterly servicing do? I'll give that one to you, Lee.
Well, in essence, the machine remains ours, and we rent it to our customers, and therefore everything to do with the technology, keeping it up and running, making sure it's maintained, all of the biostimulant that makes that digestion work, all of that is included in the monthly fee. So in essence, the message is the monthly fee is everything. There's no extra cost on top of the technology.
Okay. And Rich, in terms of the servicing and the quality of the quarterly servicing, is there anything else that needs to happen with the machine?
No, I mean, it does vary from site to site. So we've got some of the guys operating in the US, for example, they kind of like to do certain bits of what I would call general site maintenance. So in the Caribbean, the Bahamas and those islands, for example, one of those customers likes to wash their system down every day, so they do that. But in terms of the general servicing and maintenance, it's a quarterly visit by Advetec. It's a very simple process. There's very few moving parts, so it's a very easy thing to do and undertake. It's not an all-day service type activity, and the system's been designed specifically for that because you don't want or need long periods of downtime.
Okay. Next question is, do you cater for other markets across the world, and how is your technology being developed in this country and outside? So in terms of markets around the world, I think we've already talked about the fact that we've got presence in America. We have a number of sites out in the Caribbean now. Some of the islands facilities out there. We've got the unit over in the Bahamas. We've got one out in Hawaii. We've got a couple of theme parks over in the US. So the technology is starting to develop across all of those countries. In terms of how we're rolling it out, it's slightly different in different countries because lots of different countries have different types of legislation. So we're looking at each individual country as a specific area and focusing on what the legislation is and also what the customer needs are. But I think the key message is that the technology is widely transferable across different countries. We can monitor everything remotely as we do already on all of the systems, so we can see that on a daily basis. And our service engineers in each of the individual countries can support the equipment. Yep. Fine, okay. In terms of innovations and upgrades, will they be passed on to existing units? Lee?
I think that's an engineering question. But,
okay, Richard.
but in essence, I think where possible, yes. And of course, you've got a physical unit, a vessel, that enables the digestion, but then you've also got a biological treatment, and any biological advancement would be put into straight into our existing customers.
Yeah, I suppose a good example is this, isn't it?
It is, yeah. So, I mean, the beauty with the system is because we've got remote access into it, and we have learned some things from customer sites, and we have actually taken that and we've done software updates onto other people's systems. The beauty is we can do that from here in the UK. There's a SIM connection. The guys can log in, do the software update, and life carries on. We do it at night when there's no operators around, so nobody's involved in that process. So it's we do take feedback from current operations and change that. And from a biological point of view, we haven't stood still on our biological process. We used to use biology in the big white packer, which is 10 kilos of product. But through looking at that and how we dispense it and the cost of doing that, we're continually innovating within the design itself. So instead now of 10 kilograms of product going in, it's now 200 grams worth of product that get added into the process. And again, we've gone back to systems in the field. So rather than having to send 10 kilograms of product across the world, which costs money, it's now 200 grams of product that we can send, and it's far more cost effective for us and our clients.
Last one, I think we've pretty much covered it anyway, but what happens when if the machine breaks down, and how quickly do you get it back up and running?
Good question. So again, as I mentioned earlier, we've designed the system with some dual redundancy in place. So a lot of our sensors monitoring temperature, we have dual redundancy on those. So if one goes down, another one kicks in. If that goes down, we revert to another chamber. And then we've got some defaults in software to allow that to happen. Things like fans, because it's a mechanical moving part at relatively high speed. So we have dual fans on the system. So if one goes down, we will hold frontline spares of those critical items at the site. So if there is an issue, we'll get a notification to say a fan's gone down. We can continue to run on one fan. Engineer will attend. A couple of hours later, the fan swapped, you're all back to normal. And then other than that, it's some of the electrical items over a period of time, because things like the contactors and the breakers are switching in and out. We again hold frontline spares on site so that those items can be changed should the need arise. But it's been designed that it's pretty robust.
Yeah, I think it's fair to say that, for example, the units we've had out running in the States for over 2 years look exactly the same, don't
correct,
they?
yeah. So the systems in the US have been running 3.5 years. There's systems in the Middle East that have been running longer. It's been designed to operate in a rugged environment with very little attendance. Yeah. Because the last thing you want, or the last thing we want, or the customer wants, is somebody having to come out all the time.
Brilliant.
So.
Okay, I'm going to probably call time there. I think if anybody else does have any questions online, feel free to drop them into us. We'll definitely follow those up. I'd like to thank all my colleagues for coming and helping us out today. As I said, this is our engineering office, and we hope you've enjoyed the show. It's going to be kept on the website for a wee while, so if people haven't had the opportunity to download it or you want to share it, there'll be a link on there. So thanks very much for watching, and have a good day.